Assalamu alaikum. This is Fattah again, your classmate at Advanced Data Structure course with Dr. Azreen. This is my third presentation and it will be about red-black trees. We talked in the previous presentations about two types of binary search trees, which are AVL trees and splay trees. This new kind of trees, red-black trees, is also a variation of the binary search trees, but with these properties or invariants. The first property is every node is either colored red or black. The second property is the root must be black. The third one is if a node is red, then both its children are black, meaning that these consecutive red nodes are not allowed. The fourth condition is for each node, all the paths from the node to descendant leaves contain the same number of black nodes. Meaning that if we count the number of black nodes from any node to the leaves, the number must be the same for every path. Okay, we have now a tree. This tree is not a black tree. Why? The first condition is okay, we see black and red colors. The second condition also is okay because the root is black. The third condition is okay because there is no consecutive red colors. The fourth one is not okay because if we count the black nodes from here 1 2 3, but in this path 1 2 1 2 1 2, we said in the fourth condition that the number of black nodes must be the same for every path, so it's not a red black tree. This is also not a red black tree. Why? It's obvious that here we have a consecutive red color nodes, so the third condition is violated. This is a red black tree. Why? Because all the four properties of the red black tree are satisfied in this tree. Maintain the red-black tree invariance. We need, after any update operation, either insertion or deletion, to maintain the red-black tree for invariance that we have talked about just now. For that, we need to do one of the following two operations, or sometimes both of them. One, change colorness between parent and grandparent. So the parent becomes black and the grandparent becomes red, and vice versa. The second operation is do some kind of rotation, as we learned with AVL and splay trees. In this respect, there are two main cases. Case number one, node and parent are both red. We know that this case violates the third condition. Consecutive reds are not allowed. The third condition. So what to do? We must do the appropriate rotation according to the pattern: left left, right right, right left, left right. So we need to do some kind of rotation, either single rotation or double rotation. Then change the colorness between the parent and grandparent. The second case, node and parent are both red and uncle of the node is also red. So we have three red nodes here: the node itself and its parent and its uncle. What to do in this case? This violates also the third condition. Consecutive reds are not allowed. So what to do? Push blackness down from grandparent and push redness up from parent, meaning that change the color between the grandparent and parent. If the above level is not the root, because if the above level is root, the root must be black. We will here study this example and learn which case will be violated. First, we insert the node 10. Because it's the root, it will be black. Then we need to insert 20. Okay, no matter, the 10 will be black and the 20 will be red. Insert 30. This is its position. Every inserted node must be at the first beginning red, and then if there is a violation of any invariant, we must do some action. As we see here, the third invariant is violated because we have two consecutive red nodes. What to do here? We need to do left rotation because the parent is right child and the node is also right child, right. We need to do left rotation. How to do that? Just change the rules of 10 and 20 as we see here. And also change the color of 20 to black and the color of 10 to red. Okay, this is our tree now. We want to insert 40. This is its position, the right child of 30. Here there is a violation of condition 3. It's case 2, where there is a node which is red, a parent which is also red, and the uncle also red. Here we need just to do a black change between the black color and the red color. Blackness goes down and redness goes up, as we see here. This was black, it becomes red, and these were red, they become black. Here the first condition is violated or the second invariant is violated because the root must be black, so we color the root with black. Okay, this is our tree now. Okay, we want to insert 50. This is its position, the right child of 40. Here we have two consecutive reds. We need to do some action, which is left rotation, because we have the pattern right. We do the left rotation as shown, and then change the colors between the parent and this node. So 40 will become black and 30 becomes red. Okay, this is our tree now. Inserting 15 is the right child of 10. There is no violation of any invariant, so it's okay. Inserting 18 is the right child of 15. Here there is a violation of the third invariant because we have two consecutive reds. This is a right pattern, so we need to do a left rotation as shown here. 15 becomes the parent of 10, and we need to do a color change. 15 becomes black and 10 becomes red. Okay, this is our tree now. The next event is to insert 25. 25 is the left child of 30. Here we have the second case because this node is red, its parent is also red, and the uncle also red. We need to change the color between the parent and the grandparent as shown. Parents became black and grandparent became red. Okay, now we want to insert 38. Where is its position? It's the right child of 30. There is no violation of any condition. But if we insert 28, this is its position, the right left of 25. So here there is a violation of the third invariant, which is case 2. Node and parent and anchor are red, so we need to do blackness down, redness up, which is the change color between the parent and the grandparent. So these two nodes become black and this node becomes red. But after this action, we can see that these two consecutive nodes are red, so we need to do some more action. Here we have to do a left rotation and then a left rotation between 40 and 30 okay, and then a left rotation between 30 and 20. Okay, we need now to change the color between 20 and 30 as shown here. Okay. What if we need to delete some node? For example, we want to delete 30, which is the root node for the whole tree. We do a typical delete operation as any binary search tree. We must find the maximum element in the left subtree and swap it with the deleted item. The maximum element here is 28, so we do a swap between 30 and 28 and then remove 30. We can see that all the conditions are satisfied after deletion, so no more actions. What if we want to delete the node 20? We do the same action. We must find the maximum element in the left subtree, which is 18, and swap it with 20 and remove the 20 node. After removing, we gain this tree, and we can see all the invariants are satisfied here. Okay, now we will do the same previous operations using an applet to visualize the operations. This is our visualization template to do the same operation that we have done already. The first operation was to add 10 black node. The second operation is to add 20. It will be inserted under 10. Here we have 10 as black node and 20 as red node. If we add 30, it will be the right child of 20. We need to do a rotation here because of the two consecutive red nodes. The rotation will happen and the change color between 20 and 10 also happen. The next operation is to add 40. it's the right child of 30. Here we have a node parent, a node and parent are both red, and also the ankle is red, so we need to push blackness down from grandparent to the parent. Because the root is color, we must color it again with black. The next operation is to add 50. 50 is the right child of 40. We have here a violation of the third condition because of the two consecutive red nodes. We need to do a left rotation as shown here and change the color between 30 and 40. Okay, now we will add 15. It will be inserted as the right node of 10. There is no violation of any condition, so the tree is still as it is. Okay, now we add 18. It will be added to the right subtree of 15. Here we have a violation of the third invariant because of these two consecutive red nodes, so we need to do a left rotation, change the rows between 10 and 10, 10 and 15, and change also the color between them. That's it. Now add 25 to this tree. Its position will be the right node of 30, the left node of 30. Here there is a violation of the third invariant, and it's case number 2, where we have the node and its parents and its uncle all are red nodes. We need to do a change color between the parent and the grandparent levels, as we see. Now we will add 38, which will be added to the right subtree of 30. Here there is no violation of any invariant, so we will advance to the next operation, which is adding 28. If we add 28, it will be positioned at the left subtree of 38. Sorry, at the right subtree of 25. Now we have a violation because we have the node, its parent and its anchor are all red, so we need to do a color change between this level and this level. After we change the color between these two levels, we have another violation of the third invariant because of these two consecutive red nodes. Here we need to do the rotation action between 30 and 40. After that we need to do some more action because also there are still two consecutive red nodes, so the next rotation will be between 20 and 30. After these two rotations, we change the color between 20 and 30. Now the tree is a red black tree. Okay, now we will do the two deletion operations. First we will delete 30. Sorry, delete here. There will be a swap between 30 and 28 as we mentioned, and 20 and this node will be removed because there is no violation of any invariant. The tree is still a red black tree. Now we will remove the node which contains the value 20. We will do the same action, swap between 18, which is the maximum of the left subtree, with 20, and remove this node. Also the tree is still satisfied with all the invariants of the red black tree. At the end of these demonstrations of AVL and splay tree and red black trees, I would like to thank Dr. Azrin very much and all of you respected friends for paying attention, and I highly appreciate your patience regarding the bad recording and the bad language, and I hope to see you again soon.